We know the reducible representation of a set of functions carries the information about the dimension and the types of irreducible representations present. Suppose we want to describe all three molecular movements that are translational, rotational, and vibrational motions of a molecule. For that, we will consider the coordinates of all the atoms in the molecule. For example, let's say ammonia. It belongs to a C3V point group. And it has 4 atoms, so its rotational, vibrational, and translational motion can be defined by a total of 12 coordinates. Here, our bases are Cartesian axis X, Y, and Z. Since we have a total of 12 different coordinates, our reducible representation must be a 12-dimensional. If we reduce it using the character table of C3V and using the reduction formula, we will find that the reducible representation contains 3A1 plus 1A2 plus 4E. Here, we have 4 one-dimensional, which are 3A1 and 1A2, and 4 two-dimensional, which is 4E. If we sum the dimensions, we will end up with 12. All molecular motions can be classified using these irreducible representations, and these are partitioned into translational, rotational, and vibrational contributions. If we see the character table of C3V, the X and Y axis transform like E, and Z axis transforms like A1. So, we can say our translational motion can be described by A1 plus E. So out of the 3A1 and 4E, 1 from each is dedicated to translational motion. It means translation along Z belongs to A1 as it remains unchanged under all symmetry operations, whereas translations along X and Y belong to E because they transform into each other under the symmetry operations of C3V. Similarly, in rotational motion, we have Rx, Ry, and Rz. From character table, Rz transforms as A2 and Rx and Ry transform as E. This Rz rotation is around the principal axis, which is AC3 axis. Molecule spins like a top. All atoms move in circles around Z. If we apply the C3V operations to these rotations, for example, under reflection, direction of rotation reverses, the clockwise becomes anticlockwise, and the character becomes -1. So, it comes under A2. So rotational motion transform like A2 plus E. Now the remaining irreducible representation represents the vibrational motion. So, the irreducible representations for the vibrational motion are 2A1 plus 2E. Means, to symmetric type vibrations, A1. To doubly degenerate vibrations, E. Each corresponds to a specific pattern of atomic motion. Imagine the atoms are moving in a certain way. Now apply symmetry operations and check whether the motion looks exactly the same or changes. If it remains identical under all operations, it is totally symmetric. If it changes or mixes with another motion, it belongs to another representation, like E. In ammonia, pick one hydrogen, say H1. H1 moves outward. H2 and H3 move inward. This is one asymmetric stretching motion. Now rotate the molecule along the C3 axis. After rotation, H1 becomes H2. H2 becomes H3 and H3 becomes H1. Now, H2 moves outward and others inward. The motion is not the same as before. It has changed into another motion. So this particular motion is not totally symmetric. Similarly, we can predict the nature of all vibrational motions and assign the irreducible representation to it. This is the fundamental way of assigning the irreducible representation to the molecular vibrations.